Right. All right, this one here, yep. So you can find the tail expansion of exponential around 1 as well, yep. Which is something, yeah. Where's that? You can find that around 1, yeah, this one here, this one. So this is the tail expansion of exponential around 1. You change the point, right? Earlier we computed the tail expansion around 0, now around 1. The center is 1 now, right? So this is the tail expansion. Now you can find the radius of convergence. Then you can identify the interval of convergence. Again, you get the radius. What is? I think you get the radius of convergence is infinity. That means this power series or this tail expansion converges to this function for any x, for any point in the real number system. All right, so yeah, so these are, I think you have learned this thing on the differential equation course, right? These are not new things, right? Yeah, so using the ratio test, you can find the radius of convergence, which is 1 over this thing, yeah, infinity, yeah. And if you, yeah, you know that. All right, so now we know that if you are given a function, all you need to, so if you are given a function, you can find a power series. So you have to check whether it is infinitely differentiable or not at this point, at a certain point, right? So we know that exponential, sine, cos, all are infinitely differentiable at anywhere. Then you can find Taylor expansion around any point, right? All right, we know that. What else do we? Yeah. So yeah. So we have discussed. Yep, they already learned these concepts. Exponential has about, yeah. So when does this? Okay. All right, this one is very important, right? Here, this is our original one, right? This is your function, and this is your Taylor series, right? Here they prove this one converges to this. That means if you take the difference between these two, you can show that the limit of this this is called remainder of Taylor expansion, right? So this is called remainder. That means you take the difference between this one and that infinite, this power series, right? So if you take the limit, so you want to see what will happen to this function as n goes to infinity. You can show that this function goes to 0. You can show that, right? That's why, yeah, over this interval, you can show that this function goes to 0. There is no distance between these two if you consider infinitely many terms. That's the thing, right? If you consider infinitely many terms, so if you consider entire infinite series, so both are the same. But when you deal with computer, you have to cut down from somewhere. That's the thing. So we have to find a better approximation. That's the thing. So we have finite, computer has finite abilities, right? So computer cuts down this infinite series from somewhere. That's the thing. Okay. All right. This one is very important, right? This is called Taylor theorem on the remainder. Yeah, so this is called remainder. Remainder is the difference between the original function and the Taylor polynomial. This is the Taylor polynomial, right? That means you consider the first n term, the partial sum of this infinite series. So I forgot to mention that one. Yeah. So yeah, this is the, yeah, I think that one. Yeah, let's look at the notation. I think degree of t. Yep, that's the thing. Yep. Yeah, this is called Taylor polynomial. That means you cut down this infinite series from where? From n plus 1. Yeah. So this is a polynomial, and degree of this polynomial is n, right? So if you look at the distance between the original function and the Taylor polynomial, that means partial sum of this power series. So if you take the limit, and goes to infinity, right? So you can prove that you can prove that. So this function goes to 0. That means if you consider all terms of this power series, there is no difference between these two, right? But there exists a difference, or there exists an error if you truncate this power series from somewhere. So that's the thing. So we find a better approximation to this function. That's the goal of today's session. So we know that we have finite resources, or computer doesn't have infinite memory to calculate this infinite sum. Computer truncates this infinite sum from somewhere, right? So we do some kind of research. So we find a better approximation. That's the thing, right? All right. For that, this theorem is very important, right? This theorem. So let's read out this. Yeah, we know this one. That this means what? If you consider the entire power series, there is no difference between the function and this thing over this interval, over the considered interval. Where's the interval? This one. So this is the interval of convergence. You can find R using ratio test. Then you can find this interval. Over this interval, this power series converges to F. So here we consider a part of the partial sum of this power series. Now we check. Now we measure the distance between the original one and the partial sum. So, all right, that's the thing. Okay. So, all right. So this is the theorem. Let's look at the theorem. Yeah, this is called Taylor theorem on remainder, right? Yep. Do you have any questions? So I forgot to, yeah. Do you have any questions? Did you understand? Because you have done Taylor series. Why do we consider Taylor polynomial? Because we don't have infinite memory in our computer to compute this infinite series. So we have to consider a finite series or power series or polynomial, right? So that's why we compute the error. This is called error or remainder. You can say remainder. So this is the original complicated function at x, right? And this one is the partial sum of this power series. And we are going to find a better Taylor polynomial or partial sum, a Taylor polynomial. This is a polynomial, n degree polynomial, I think, right? N degree polynomial. So we are going to find a better approximation to this original one, right? So, all right. So let's look at this theorem. This theorem is very important right here. So we know that our function, let's assume this function is infinitely different or n plus 1 differentiable. Yeah, n plus 1 times differentiable on this interval, let's say, yeah, on this interval, right? Let's assume that, right? Let's assume that we know that this function is infinitely differentiable at where? This function is infinitely differentiable at a, but we don't know whether it is infinitely differentiable over this interval, right? We don't know. Let's assume this function is n plus 1 times differentiable over this interval, right? Let's assume, right? If this the n plus 1 derivative of that function is bounded, that means you can find uppercase m, right, over this interval, then, right, then this remainder, that means the difference between the original and the nth order Taylor polynomial is, you can show that this one, that the absolute value of the distance between the original and the Taylor polynomial is less than or equal to this quantity, right? So m divided by n plus 1 factorial n plus 1 times x minus a to the modulus of x minus a to the n plus 1 over this interval, right? This one is true. You can prove, I think, if you do pure math, I think you can show this one is, this inequality is true. Now we consider this one, right? We consider this one for our octave program, coding, right? All right, this is the concept we are going to. So let's do a small example, right, to understand this theorem. Right? Okay. All right. All right. Do you have any questions? Does this make sense to you, or do you need more explanation? Any doubts? Or what do you think? It's time to, yep. So I want to confirm whether you understood or not. So did you learn any new concept? I think you already learned, I think, Taylor expansion, and you know the partial sum. So here, this is called Taylor polynomial. This is basically a senior. I think you follow the pure math. I think this is the partial sum of this power series. All right. This is called, since this is a Taylor expansion, we give a name. This is a Taylor polynomial. That's it, right? So now we check the difference between the original and this Taylor polynomial, and we investigate the error between these two. So we have to grab a better approximation or better Taylor polynomial to do our computation, because We don't like to deal with this complicated function, because that's why we consider this approximation. So if this error is very low, very little, if this error is very little, right, then this is a better approximation to that. This is a better approximation to this function, because we are dealing with computers, right? We have finite limitation. You know, we have finite resources. If you have infinite capacity memory, then you can do this calculation, this infinite sum. But we can't. We have finite resources, so we have to truncate this infinite at a certain place, right? All right, so to understand this theorem, let's do a small question, right? Okay, consider this function f of x. No, this one, sine of x, right? So we know that sine function is very nice function. It's so smooth, infinitely differentiable at anywhere, very smooth, very nice function, right? So when you differentiate this sine function, you get cos or negative cos, negative sine. Yeah, what you, so how do you find? Yeah, so the n plus, or you have to find, so you have to, yeah, what is that? Yeah, you have to calculate this one, n plus 1 derivative of sine. So sine, you know that when you differentiate sine, you get cos. Then when you differentiate cos, you get minus negative sine. When you differentiate negative sine, you get again negative cos. And that means, right, that means the n plus 1 derivative of sine would be one of these, right? Either plus sign or minus sign of x, or positive cos of x, or negative cos, one of these, right? So you know that this is an altered, these all four functions are bounded by positive 1 and negative 1 plus up, that, yeah, these four functions are bounded by plus or minus 1, right? Bounded by plus 1 and minus 1, right? So therefore, the absolute value of this nth derivative is bounded by this number 1, right? M is 1 here, right? Okay, for any x, right? For any x, right? Now let's assume the Taylor expansion of sine around 0, which is Maclaurin. So what is the Taylor expansion? We computed before, right? Computed before, where's the so where's that infinite? Yeah, this one, I think. Yep. So yeah, this one here, infinite series. Yeah, this is a power series. Yeah, infinite. There are infinitely many terms, right? All right. So there are infinitely many terms. This one is the tail expansion of sine around zero, which is called, yeah, Maclaurin series of sine, right? All right. So you know that we cannot deal infinitely terms. Yeah, we cannot deal with infinitely terms. We have to consider finitely many terms. First few terms only, right? Or partial sum, right? So let's, okay, here we go. Yeah. All right. So we identified what M is, right? And the, yep. So this R Sub n is the distance between the original function. Our original function is sine of x. This is the partial sum of that power series, right? Okay, so that one is bounded by m. Here is 1 over n plus 1 n plus 1 factorial times the modulus of x minus this the point. The point is 0. We consider, right? We consider the tail expansion of this function around 0. That means Maclaurin series. Yeah, a is 0 here to the power n plus 1. Right? This distance. That means the distance between the original function sine of x and the partial sum of that Taylor expansion is bounded by this one here. So this one is very useful, right? This one is very useful. Let's do a small question. Yeah, to understand that concept. Where is that? I'm not sure whether you have done this one before, right? Let's find this one now, right? What is the minimum number of terms in the Taylor expansion of exponential around 1 that needs to be used to compute e to the 2 with an accuracy of 10 to the minus 2. All right. So how many terms we should include to approximate this one with this accuracy? So now, we know that exponential, we know that. So first find the Taylor expansion of x around which point? Around 1, right? So Taylor expansion would be around 1, e1, I think this one, yeah. X minus 1 divided by factorial or something like that. E1, right? X minus 1, because we are finding Taylor expansion around 1, right? This goes on, right? This goes on infinity. Now, so this question, what is the question? What is the minimum number of terms of this infinite, this power series or infinite series? There are infinitely many terms. What is the minimum number of terms in this Taylor series around Taylor series of EX around 1? That need to be all right. We use this one to compute. All right, we found the Taylor expansion around 1. Okay, we get something like this. All right. So now we are going to find this is your this is your this is your Taylor expansion, right? Infinite series. This is your infinite series. Yeah, you get something like this. Yeah. Now we use the first few terms of this infinite series to approximate this value, e to the t. Yeah, e to the 2. Yeah. Now, this is x equal to how? Yeah, e to the 2 is here. This is your e to the 2. But we have to find the minimum number of terms we have to consider, right, to get this much accuracy. So we know, right here, look at this. Yes, that. All right, remainder theorem. All right, now, yeah, this time you can use the remainder theorem. Where's that? Remainder theorem. Okay. All right, this one. So, okay, the distance between the original, yeah, our original is exponential. And the Taylor, how many? We don't know how many terms we have to consider. Let's say Tn, right? Let's say Tn, right? We don't know how many terms we have to consider. This value, the distance between the original and the Taylor polynomial of exponential around 1 is less than m over n plus 1 factorial x minus point is 1 now, right, to the power n plus 1. Let's figure out this one. Yeah, x when 4 x minus 1 less than or equal, yeah, d, we have to consider d. All right, let's go back to our question. So this one here, m minus m divided by n plus 1 factor. Okay, 5:30. After this, we had to use octave, right, for these things. Okay, all right. So this is infinite series, all right. So that, let's say the original distance between original function and the Taylor polynomial, that means the finite terms. We don't know how many terms we have to consider. Let's say n, right? Less than or equal m divided by n plus 1 factorial x minus 1 to the power n plus 1, I think, right? Over the interval 4, x minus 1 is than d. Let's decide this d, right? Okay, here, look at this. We want to approximate this one with this thing. Okay. Now we know that exponential function is an increasing function, right? So, right, this is E1, right? This is E1 and this is E2, this one is E2. All right, so the if you consider 1 to this interval between 1 and 2, then the bound, so this one is an upper bound, right? Right, so x minus 1, if you consider this interval d is 1, that means you are considering x to 0, this interval there, 0, right? Okay, over this interval, we can say that function exponential function is bounded by e to the 2, right? E to the 2, right? So therefore we found m there, right? So m is e to the 2. Okay, here d is 1, I think. Here d is 1, right? Here we just consider this interval. This is your 0, and this is the center, and this is, and the radius is 1. Radius is 1. So x minus 1. So this is the center, and this is the radius 1. So when we expand this, you get this one. So now we have to consider this interval. Over this interval, that function is bounded by e to the 2, right? Okay, you grab this value. Okay, now you can sub this number into here, right? So this is, yeah, the original distance between the original and the Taylor polynomial is less than e to the 2, yeah, less than e to the 2 divided by n plus 1 factorial x to the, yeah, this one, right? So here you know that x minus 1 is less than 1, then right, then we can write e to the, yeah, then n plus 1, yeah, n, don't write that, e to the 2 divided by n plus 1. So we have to find the number of terms we should consider of this Taylor expansion to get this accuracy. All right, e to the 2 divided by n plus 1 factorial should be less than 2 to the power, yeah, 2 to the, yeah, let's, don't have space to write there. E to the 2 divided by n plus 1 factorial should be less than or equal to, what is the accuracy? We need this accuracy, 10 to the minus 2. Then you can find, this is 100 times e to the 2. I'm not sure whether this is, yeah, plus 1 factorial. Then you can find n here. Just subbing numbers, sub n equal 1. No, factorial. I mean, what is the value of this one? Yep, let's, I want to wait a second. I'm going to plug my keyboard. Wait a second. Don't have only one USB port. So time is flying, yeah. All right, let's go to Octave. Let's compute. What? Can someone say what is the minimum value of n? All right. I think you can do this, right? All right, let's find factorial. Let's find factorial, right? What is the value of factorial, right? Oh, how to find that factorial? Do you know how to find factorial, right? What is the built-in function? I don't remember yet. Yep, Puvdika, what is the built-in?
So you have to write factorial and within brackets 7. Factorial is the function.
Real, this one?
Yeah, and then 7.
Let's see. All right, thank you. Let's see, 7. Choose X, 5, 6. All right, here so this value is 738 point something, but we get, yeah, so factorial 6 is 720. We close pretty much. So definitely factorial 7. Yeah. So this one is greater than or equal to this, right? So the minimum value of n would be what? Yes, that will. So factorial 7. Yep. So factorial 7. Yep. This. So that means 6 plus 1 is 7. This one satisfies. Yep. 10 to the 10 times e to the 2 less than or equal to this. Yep. All right. This one is the minimum n. That means we have to include at least first 6 terms of this infinite series to get this much accuracy, right? So if you add a lot of terms, then you are good, but you have to add at least 6 terms of this infinite series. This one, first 6 terms, right? First 6 terms. If you add more terms, then good, but it is very computational costly, right? So it is better if you add at least first 6 terms of this infinite series to get this much accuracy, right? So that's the thing, right? Now let's all right, let's play with Octave, right? Okay, let's so can you open your Octave window? All right, let's play with Octave. Let's see how to use Octave to compute Taylor series, Taylor polynomials, right? How to find Taylor polynomial or Taylor series, Taylor polynomials. All right, clear the window. So have you, have you dealt with symbolic package before? Octave symbolic package, do you know? Have you used this one before? Symbolic package? Anyone? No, so right. Okay. All right. So let's try to download this package to your computer, right? So just go to LMS. I think go to your LMS. So you can find this document. If you go to LMS, just log into your LMS, right? Yeah. You can find this document. This is activity, first activity. Yeah. This one. Yep. So here, download this. Open this one. Yeah, we will get this one, right? So if you want to install, so definitely you have to install symbolic package. So because you are playing with symbolic items, or you are playing with symbolic things, so because we have to include symbol X. So without this package, you cannot do that. So you have to download this package first. If you click on this link, if you click on this one, it will automatically go to this page, Octave page, right? Then you can download this package. So there are many packages here package. So there are many Android Audio, there are many packages you can download, right? But here we for our, where's that? Yeah. So for our one is Symbolic package. Symbolic. All right, this one here. So because we have to play with symbols X, Y, and Z, right? So go to this one, or you can download from here, right? So go to Symbolic. So you have to download this file, right? Just download that. So after you download that one, you will get what you get. So you will get something like this. Yeah, this one, right? Symbolic. So have you downloaded that file? So did you download that? Just go there. I think this is about 40 MB file. I'm not sure. Yeah. Right, download that one. All good. Did you do that? Did you download this package? Cancel. Need your response. So download that. Please download. Yes. Is it available for Mac OS? Yeah, it is available. I think you can use this one as well. I think this is for Mac users. I think we can. I think we Windows users. We can. This can be used for Windows users as well, right? I think this extension is Mac, I think, right? Mac OS. Yeah, download that. And let's see how to install that one, right? Did you download? So I have to download in that file onto your hard drive, right? Now we are going to install that package on your computer, right? So to install that symbolic package, so open your Octave window. Yes. All right. And right, or you can change the directory to where your downloads are, right? You can change this directory, right? From here, can change, or you can copy your file to one of folders of in Octave folder, right? So did you do that? You can change the directory from here to where your downloads are, right? So know how to change the directory, right? So do those steps. So then you have to type on the command, either in the command prompt, pack package. This stands for package pkg pack space install the name of that file, the name of the file you downloaded from Octave site, right? Right. So right, have you done those? Did you download the file and an error is coming? Oh, what is what? I can see your screen. Ubudika, is this the right method to install or install that package?
Yes, I think so.
Yes.
Deshan is more familiar with it. Deshan, is this right?
What did you didn't hear that? Yep. Hmm?
Actually, I downloaded it around months ago, so I can't remember whether it was the
Oh,
method.
okay. Right. So you don't need to have WinRAR. WinRAR, you don't need that. You don't need to extract the download file. You just yes, my one. Let's look at Octave. This is yeah, this Octave. So this is my so I copied that download file to this here in Octave folder. So my one is in Octave folder, right? So now I change the directory. This is the directory. Yep, we can cancel this. Yep, let me. All right, it is already in. We are already in Octave folder, right? Don't need to change. If you want to change, you can do that, right? Change your directory to where your file is. I think you have to locate the file, or you can copy that file to this directory, Octave directory. Yeah, this is so. This is the file. It is about, I think, 45 MB. Yeah. Then after downloading that, right? So we have to change. You don't need to change the name. Or you, I'm not sure. I didn't change the name. I didn't change the name. I copied the name. There is a Octave down. T T. Yeah, Octave here. I didn't change the name. Or you don't need to change the name, right? You can take this name, just rename. Yeah, copy this name. Yeah. Copy this name with this extension. I think I copy that name, or you can copy this one here. Install package. So I am in. I am in the right directory. So in this directory, I copied that. Yeah, I copied that file to this directory, right? So now I can install the package. So I'm able to install that. Let's see. I'm not sure whether I install that. Let's see. Yeah. It's installing. I think you don't need to put yeah, gz.gz. It's installing. Let's see that it takes time on. Have you done that? Yeah. All right. For information, previous version, because I already installed that, right? So how do you install that? You have to write, yeah, this one, yeah, pkg space install, and this one without this extension. I have to put that one. So don't put this extension. Just copy this one only, right? Copy that. Let's do it again and paste that and enter. All you need to do is you have to select the right directory here. So in this directory, in this folder, I copied the relevant file into this folder, right? So you have to change that. Right. It's working now here without any errors. All right. So have you done that step?
Excuse me, sir.
Uh-huh.
Deshani, there is another method without downloading the folder file. Without that, there is after we have to connect to the internet and then type a code. Shall I
Okay.
send you that?
Yeah, sure. I will give permission to share your screen. All right, stop sharing. Share your screen. You have to give permission. Yeah. Where is it then? Yeah. All right. Now you can share your screen. Yep.
Give me a second.
Stop.